In the field of natural language processing, text embeddings play a crucial role by representing pieces of text as dense vectors that capture their semantic meaning. These embeddings are essential for tasks like measuring semantic textual similarity or grouping texts and clustering. However, traditional embedding models often generate a single, universal representation for any given text, which can struggle with the inherent ambiguity in language. For example, consider 3 short reviews. The first says, "This camera is one of my favorites." The second states, "This smartphone cannot capture high-quality images." And the third notes, "Best fish I have ever had." At first glance, the first and second reviews discuss similar product categories like electronics, but they have opposite evaluations. Meanwhile, the first and third reviews differ in categories, one about a camera and the other about food, but they both express positive sentiments. Without any additional context, it's challenging for a universal embedding to decide whether the first review is more similar to the second or the third. This is where conditional text embeddings come in. They are a more advanced representation that adjusts the embedding based on a specific aspect or condition, effectively capturing shifts in perspective. For instance, if we condition on product category, the embeddings might highlight similarities between the camera and smartphone reviews. But if we condition on star rating or sentiment, it might align the camera review more closely with the fish review. Previous approaches to conditional text embeddings, as proposed in studies from 2023 and 2024, have relied on supervised methods. These typically require extensive training data tailored to tasks like conditional semantic text similarity. This means gathering domain-specific datasets and fine-tuning large language models, which is labor-intensive, resource-heavy, and often limited to specific languages or domains. Additionally, some methods involve instruction fine-tuning, where models are adapted for particular tasks by inputting prompts, but this still demands significant amounts of manually or automatically generated data, making it time-consuming and costly. To address these challenges, researchers Kosuke Yamada and Peinon Zhang from CyberAgent in Japan introduced a novel method called PonTE, which stands for Prompt-Based Conditional Text Embedding. PonTE is an unsupervised approach that leverages the power of causal large language models, models like those based on transformers that predict the next word in a sequence, without the need for any fine-tuning. Instead, it uses carefully crafted conditional prompts to generate effective embeddings on the fly. At its core, PonTE works by feeding a prompt into a causal language model and extracting a hidden state vector from the model's internal layers. Specifically, the method takes the hidden state of the last token in the prompt as the conditional text embedding. The prompt is designed to enforce 2 key restrictions. It must express the target text in just one word, and it must do so in terms of the specified condition. For example, if the target text is, "This camera is one of my favorites," and the condition is product category, the prompt might look like this. Express this text, "This camera is one of my favorites," in one word in terms of product category. The language model then processes this prompt, and PonTE extracts the relevant vector from its output. This process compresses the textual information in a way that's oriented toward the condition, creating an embedding that reflects the desired perspective. This idea draws inspiration from another method called PonTE, but PonTE adapts it specifically for conditional embeddings. By using prompts like, "This text," "target text," means in one word in terms of condition, or variations thereof, PonTE ensures that the generated embeddings are versatile and can be applied across different domains and languages without prior training. To evaluate PonTE, the researchers conducted experiments on 2 main tasks: conditional semantic text similarity and text clustering. In conditional semantic text similarity, they compared how well PonTE could measure the similarity between texts under various conditions, using datasets that included ambiguous examples like the ones mentioned earlier. The results showed that PonTE performed comparably to supervised methods, even though it didn't require any fine-tuning. This means it could achieve high accuracy in determining, for instance, that 2 texts are similar in terms of sentiment but not in terms of category. For text clustering, PonTE was tested on grouping texts based on conditional aspects. Here, too, the embeddings proved effective, demonstrating that they could organize texts into meaningful clusters without the need for labeled data. The researchers highlighted that PonTE's embeddings maintained the semantic integrity of the original texts while adapting to the conditions, making it a flexible tool for real-world applications. One of the standout features of PonTE is its interpretability. Unlike black box embeddings from some models, PonTE allows for easier analysis. For instance, by examining the word generation following the prompts, researchers could see how the model interprets the condition. In the example from the paper, prompting the model to express texts in one word under different conditions revealed clear shifts in focus. Additionally, embedding visualization techniques, such as projecting the vectors into two-dimensional space, showed distinct separations based on conditions, making it straightforward to understand and debug the embeddings. Overall, PonTE represents a significant step forward in making conditional text embeddings more accessible and efficient. By harnessing the pre-existing capabilities of causal large language models through simple yet effective prompts, it bypasses the barriers of data collection and computational demands. This approach not only matches the performance of more complex methods but also opens up possibilities for broader applications in areas like sentiment analysis, recommendation systems, and beyond, where understanding context-specific meanings is key.